Okay, now if you go to
Oh,
present mode. Yep, now it's all good.
yeah,
Yep,
perfect,
yep,
perfect. Okay,
one.
okay, thank you.
Great.
Sorry for this one. And this week, today I'm going to talk about this Trustworthy Retrieval Augmented Chatbot. This our recent work on providing guarantees for RAG systems. But before diving into the technical details, I would like to put this research into a much bigger picture, which we termed this one as developing efficient, trustworthy AI system. I will motivate this topic by my theory about giving a talk. Suppose that you're given a talk and you would like to get as much attention from the audience as possible. Then, to some extent, you will have this trade-off. This trade-off before sophistication and attention, right? So if you give a talk in a very straightforward, very only give like very limited detail, people will think, well, your talk is too naive. I can take a little thing from this, and they will lose their attention. Or if you give your talk in a very complicated way, sophisticated way, people cannot follow you. They will lose their interest as well. So in order to get as much attention from them as possible, you would like to find out the sweet point, so that you will make a good balance between sophistication and get the attention from them.
Sorry,
But
Shuo, can I interrupt you for 1 second? Just
oh,
1 second. Could you tilt up your camera a little bit because
oh,
yeah, now it's
sure,
better. Yeah, sorry.
sure. Yeah,
Thank you.
no worries, no
Yeah.
worries, no worries. And but if you actually think about this problem in practice, the landscape of the attention, of the trade-off between the sophistication and attention is complicated. It's by no means known to us, and it is very likely non-convex. And we may have different kind of objective here. We may have attention, or we may give a talk to actually ask for some funding. If we actually, getting back to the trustworthy problem, we will have the similar trade-off. When we talking about trustworthy system, we actually sometimes will run into this kind of trade-off, a trade-off between guarantee and efficiency. For most of the work, they focus on getting the guarantee for the system, and they do not explicitly consider about efficiency. But I would claim that if only with the guarantee and with a low efficient system, you may run into the problem that you may have a very fancy mathematical guarantee, but your output from your algorithm or the trustworthy system may not be that useful. Let me give you one example. So this is some result from our previous submission from previous work. We want to provide some guarantee for object detection system, right? So, and the motivation is similar. We would like to get improved the efficiency, which in this sense is the size of the bounding box, while providing a guarantee that our bounding box will be able to cover the true bounding box, which is in white with high probability. Without explicitly considering about the efficiency, we can see that the bounding box is looser, is larger than those ones when we actually consider about the efficiency. And such efficiency improvement could be very important if we utilize such object detection result for navigation, for autonomous driving, for example, because a tighter or smaller bounding boxes enable those autonomous driving systems to employ more ambitious aggression task planning. So this actually demonstrates the efficiency, the importance of considering efficiency when constructing those trustworthy systems. So to summarize the motivation for this bigger picture, we would like to obtain high efficiency of machine learning system while guaranteeing its trustworthy. And this trustworthy could be, for example, true label coverage, or this bounding box cover the true bounding box. Okay, so this trustworthy retrieval augmented chatbot is actually one of the work that we put into the efficiency trustworthy system development. The motivation is as follows. I guess it's acceptable for us to claim that large language models are really powerful. And here's just very I demonstrate this one to many people. We can see that ChatGPT or GPT-4 obtain very outstanding result in those standard exams. They have reached human level. But they actually hallucinate a lot. They may make up some they choose quote unquote truths by themselves. Let me give you some example. For example, here the user may input when did the Da Vinci paint the Mona Lisa, and we can get the result from ChatGPT that Da Vinci painted the Mona Lisa in 1815. But it turned out that this generated answer is wrong, right? So the Mona Lisa was actually painted between 1503 or 1506. So ChatGPT just generated that claim without any hesitance, but it's actually wrong. If you trust ChatGPT blindly, you may probably run into some problem. This is another example, very interesting example, which demonstrate that if you really trust, put all of your confidence with chatbots, you may run into another more serious problems. Here we ask ChatGPT to actually generate some code for us, that we can see that after generating the code, we can see very biased code from ChatGPT. All of these examples actually demonstrate that ChatGPT, if we trust it blindly, may get us into some serious trouble. And this hallucination is actually a huge problem that we need to solve, or at least reduce. And we can see a lot of those attentions, warnings from those public media as well, from CNN, from Bloomberg. They all complain about this hallucination. So the hallucination is a very serious one we need to solve. There are some excellent works reducing the hallucination in the literature. One of them is actually the retrieval augmented generation. The base or RAG. The basic idea of a RAG is as follows. When you get a prompt and a query, you would like to retrieve or get some related passage from some knowledge corpus. Say, for example, Wikipedia or the website, the internet. And then you will retrieve those passages using this retriever, the dense passage retriever from Meta. After getting those related passages, you will submit your prompt, your query, together with the passage to the large language model. For example, you may ask who is the president of the United States currently. You will retrieve the passage from Wikipedia page of the United States. And you will submit your prompt and the Wikipedia page to ChatGPT, and ChatGPT will generate the answer for you based on the context. And the basic idea, that the hypothesis is that after observing related passage, related context, large language models will be able to generate more accurate answers for you. So this is the block diagram of RAG. And here's one example. Say, for example, if you ask this question, the retriever, the passage retriever will actually retrieve related passages for you. Among them, one of them will be, or some of them will be quite relevant to your query. And you will submit each of this query and passage pairs to ChatGPT. And based on this combination, ChatGPT will probably be able to answer your question correctly, return the correct answer. But there are some limitations with this architecture, especially for the retrieval part as well. So this is the result I got from the dense retriever website on GitHub. And we can see that this retriever is not perfect. Not perfect in the sense that given a query, for example, if we only retain the top 20 passages, the rate that the most relevant passages is contained within these 20 retrieved passages is only around like 80% of the time. In other words, given a query, and if we only retrieve 20 related passages, the chance that you miss the most relevant passages will be like as large as 20% of the time. It's not perfect. And also, similar to all this learning-based data-driven method, there's no guarantees with respect to the performance. So our goal of this project is actually as follows. We can state it in the following way. We would like to construct an efficient semantic prediction set while guaranteeing end-to-end coverage level in RAG. We would like to construct the semantic set so that the set is guaranteed to contain the true label for the query with high probability, and the probability is specified by the user. Here's just one demonstration of the resulting set. Given a question, what is the second movie of the Pirates of the Caribbean? We would like to construct this kind of answer set, which contains different kind of answers. But we can guarantee that within this contained answers in the answer set, the true answer will be contained. For example, we contain the exact same answer. We also contain the answers with similar semantic meaning. For example, this one. It is not the like one-to-one mapping, exact match, but we can clearly see from this one that these two answers are the one that we included in the set, and the reference answer, they have the same semantic meaning. So here's a like intermediate review about what we've discussed so far. We discussed the trade-off between guarantee and efficiency, and we discussed the threat of hallucination from those large language models, and we discussed the retrieval augmented generation architecture and its limitation. And I also stated our goal. And I guess it's a good time to pause and to ask, are there any questions or comments or unclear points from the audience?
For me, it was all clear.
Okay.
Very clear.
Yeah, perfect.
Thanks.
Yeah, of course. Then let's dive into the technical details of our work, which we term as TRAC, Trustworthy Retrieval Augmented Chatbot. First, I want to give an overview of our method. It consists of two main steps. The first step is actually to construct set with provable guarantees. We would like to construct two kind of sets. The first one is what we call retriever set. So the retriever set will guarantee that given a query, this retriever set will contain the most relevant passage with high probability. The second kind of set we are going to construct is called chatbot set. For this chatbot set, we can guarantee that given a query and its most relevant passage, chatbot set will contain the true answer with high probability. And then by combining these two sets, we can give an end-to-end guarantee in the following way. Given a query, the resulting prediction set will contain the true answer with high probability. So this is the first step. This step serves to provide a guarantee. The second step is actually serve to improve the efficiency. We would like to allocate the error budget for the retriever and chatbot set so that some user-specified efficiency function, for example, the size of the set, can be maximized. The efficiency will be maximized, or the size will be minimized after improving the efficiency. So this is the two-step of our method. Let me dive like a little bit detailed about how this two steps works. The first step is actually to obtain the coverage guarantee. And then first, we obtain the guarantee using conformal prediction. And I guess to the audience, the conformal prediction is already a very familiar concept. But here, I would like to demonstrate this one from using another perspective. This is my understanding. So the basic idea is that given X as a sample space, and alpha as the allocated error level, and we would like to include the samples into the prediction set so that all of those samples will contain at least 1 minus alpha portion of the whole sample space. The basic idea of conformal prediction is that we would like to design this non-conformity score, right? And we will include all of those X into the prediction set whose non-conformity score is below this red line. This red line is actually the quantile of the non-conformity score within the calibration set. And the distribution-free part actually is with respect to the landscape of the non-conformity score distribution. We're not going to assume that the non-conformity score is subject to some Gaussian or binomial distribution. We allow an arbitrary landscape of the non-conformity score. It could be convex, could be non-convex. So this is my view of the conformal prediction. And we can actually extend this idea to higher dimensional problems. And as long as we have a scalar non-conformity score, we'll be able to utilize the same kind of interpretability to explain what conformal prediction is. Okay, so this is like a brief summarization of conformal prediction. Then in our project, in order to obtain those guarantees, we need some assumptions. The first assumption is the golden assumption in conformal prediction. We assume the distributions for the retriever and chatbot are exchangeable, so that we can actually construct a set for them. The second assumption is that given a query, the retriever should be able to retrieve the most relevant passages. The third one is that given a query and its most relevant passage, chatbot should be able to generate the correct answer, semantically correct answer. So given these three assumptions, our guarantee will be able to hold.
Can I interrupt you?
Sure.
Sorry. Yeah. Sorry. Can you elaborate a little bit more on like what exchangeability means in this context?
Yes. So exchangeable is actually it's quite hard to specify the exchangeability in the sense of language, but I guess there are two ways to though not directly, but like indirectly explain. The first one is that the distribution will be exchangeable if the calibration set we use for conformal prediction subject to the same distribution as with the testing set. So this is one perspective. Another perspective is actually we can verify the exchangeability by identifying the threshold on the calibration set and verifying the threshold on the testing set. If the coverage level is satisfied on the testing set, then implicitly the distribution of these two components are exchangeable. If that makes sense to you.
Yeah. So basically you're saying that if the empirical coverage on the test set is above the requested one, then that's already an indication of the fact that these two data sets are exchangeable.
Yes,
right?
yes. For more like rigorous or mathematical description, I guess it might be hard to specify the exchangeability like very rigorously in language.
Right.
Yeah.
Right. Yeah.
Okay.
All right. Since I have already interrupted you, I'm gonna ask one more time if you just camera a little bit up. Sorry.
Oh,
Yeah. Okay.
sure, sure,
Wonderful.
sure.
Yes. Yeah. Yeah. Exactly.
Yeah, sure.
Thanks.
Yeah, of course, of course. So this is the assumptions, the needed assumptions, and for the retriever prediction set, here are some more details about the retriever part. In our project, we actually utilize this pre-trained dense passage retriever. It's a classic one from Meta. And for each query, we actually return the top 20 related passages. So in other words, we assume that within the top 20 related passages, there will be one that is most relevant to the given query. And we use the relevant scores between the query and each retrieve the passage as the conformity score, or non-conformity score to some extent. We collect the relevant scores of the most relevant passages and use conform prediction to identify appropriate relevant score threshold on the calibration set. And I provide a tutorial demonstration of the process. Given a query, we would like to use the retriever to retrieve some passages, for example, wiki passages. And for each of the retrieved passage, we will be able to get a score indicating the relevance between the retrieved passage and the query. The higher score, a higher score indicate a higher relevance between the retrieved passage and the query. And then we would like to put the most relevant passage, the score of the most relevant passage into the calibration set. And this most relevant passage is actually labeled in the data set.
Sorry, can I also interrupt again here? One more, sorry.
Sure.
How these like two questions. Number one, how are these relevance scores measured? Like, what does it mean for a query to be relevant to a context? Like,
Yes.
how do you measure that? And number two, you said you put only the score of the most relevant context into the calibration set, or did I misunderstood? Did I misunderstand that part?
The score with respect to the most relevant passage in the calibration set. So this is a scalar. Yeah, for example, now suppose the wiki passage 2 is the most relevant one, and I only put its relevant score into the calibration set.
Okay, I see.
Okay. Yeah.
And
the first
here,
part,
sorry, the higher the score, the more relevance between the two?
Yes. Let me explain how the relevant score is measured.
Okay.
Right. So the basic idea of the retriever is as follows. They will embed the query and wiki passages to a joint embedding space. It's actually an encoder. It will encode like natural language passages or like text into a fixed length vector.
Right.
So
and then you measure the similarity between the vectors.
Yes. You can actually use like inner product or cosine similarity.
Right. Okay.
And the higher score will indicate a higher relevance between these two. And definitely there are other ways. For example, you can measure out to distance, so on and so forth. In our project, we just utilize inner product.
I see. And just one other side note, it shouldn't, in this example that you have on the screen, the wiki passage 1 be included in the calibration set because it has a higher score, 77.6? Or am I missing something?
Yes. So the two, the wiki passage, we actually have this data set. It labels which passage is actually the most relevant for this query. And in this sense, even if the passage 1 has a higher relevant score with query, which is the quote unquote prediction from the retriever, according to the label, this is not the most relevant one.
Okay.
And we're now going to put the score into the calibration set.
Okay. But you will use, but you will use only that score when you don't have the label, right?
No.
So like for all,
mm,
like for any given query, do you have the label that determines which passage is the most relevant? For all queries?
So this process is used for constructing the calibration set. We would like to construct the scores for the true labels or true passages. So the data set will provide us the query and the most relevant passage for us. Right, so this is the data set. And what we need to do is actually, given this query, we would like to retrieve top 20 passages and their scores. And use the data set to identify which passage is the most relevant one according to the data set.
Okay.
And
go ahead. Sorry. Go ahead.
And put the score of the most relevant one into the calibration set. So this is the conformity score for the true label in the classic classification setting.
Okay. Yeah, I think I get it. Yeah.
Yeah.
Yeah. Thanks.
So from my perspective, this retriever prediction set is basically an extension of the classic prediction set in classification. But the chatbot prediction set might be more interesting. Here I cited the work from Alan, the conformal prediction for language model. So so basically, the existing work, there are some existing works, and they construct set based on the generation distribution. For example, we can convert a open domain question answer into a multi-choice problem, and we can get the predicted likelihood for each of the choice, and treating this one, construct a set as a multi-choice, multi-class classification. Another work I cited here is called this conformal language modeling. They utilize the similar thing. They first collect the log probability of the generated answers and put answers into the prediction set if their log probability or probability is above some threshold. So these are a typical way to construct a set for language models. Both of them work on the token level. They consider the probability with respect to the tokens. So there are some challenges with this setting. First one, to some extent, we have to consider about the closed domain problems or multi-choice problems. Another one might be more interesting. That is, since we only consider about like the distribution or the probability with respect on the token level, answers with similar semantic meaning are actually regarded as different answers. Here I give two examples, like France capital is Paris, Paris is France capital. We can see that token-wise, they are different, right? So they have a different generation process. And it's very likely they have different like generation probability. But we all know that semantically, they are the same answer. They actually indicate the same truth. And from our understanding, we should actually consider about the semantic meaning. We should compute the confidence in the semantic level. Or in other words, treat these two ones at the same answer and put them together into the prediction set. I will explain more about this in more details in the following way. Another challenges with this process is that since these two works actually requires the generation probability, this kind of probabilities may not be available for some API. For example, if you actually utilize ChatGPT 3.5 for the chat completion task, you cannot get those log probabilities for the generated answer. So another goal of our project is actually design a method that can be utilized for general API, for an arbitrary API. And our idea is as follows. So this idea is actually inspired by another work called semantic uncertainty. given two answers, generated answers from the language model, we would like to compare their semantic meaning to see if they are semantically similar to each other. And this can be done by using by some natural language inference model or some off-the-shelf tools like a root score. If they share similar semantic meaning, we would like to cluster them together. Or if they share different semantic meaning, we would put them into two separate clusters. And then here's one example. Suppose we get this generative answers from the language model. We would like to put them into cluster them into different clusters according to their semantic meaning. The goal is that answers with similar semantic meaning will be put into the same cluster. And the size of the cluster will actually somehow indicate the language model's confidence in generating that semantic meaning. And when constructing the calibration set, we will put the confidence score, which is estimated by dividing the number of answers in the cluster by all of the answers into the calibration set. In other words, we will put the estimated confidence for the semantic meaning, the correct semantic meaning in the calibration set. If that makes sense to you. And then after collecting this calibration set, we can use conformal precision to identify the threshold and then construct the set afterwards. Then after constructing the retriever set and the chatbot set, we can combine them to obtain an end-to-end guarantee. So this is the block diagram. Getting the query, we would like to utilize the retriever to retrieve passages and construct a retriever set that can guarantee that the most relevant passage is contained in a set. Then for each of the combination of a query and the passages in the retriever set, we will ask the chatbots to generative answers for us and construct the chatbot set for that generated answers. At the end, we will collect all of the chatbot set with different this query passage combinations and aggregate them together so that we can reduce some of the semantic meanings, reduce some of the answers that shares the same semantic meaning.
Sorry, can I interrupt one more time here?
Sure.
Yeah, in an earlier slide where you showed the samples of like generated answers, there were some repetition in them.
Yes.
Is that because you may get the same correct answer generated on different contexts?
No. So
No?
for this, no. So we do the following thing. For each of the passage, query and passage combination, we will ask ChatGPT to say generate 30 answers for us.
Right.
So this is more like a Monte Carlo sampling. We will sample the distribution for 30 times.
Okay.
And this is one example of the generative answers for one query passage combination.
Right. But then why is it possible that you get like in your final predicted set? Why do you have repetitions?
You mean this one?
Like if you go in one very early slide, very early slide, but I think back.
That's this one, right?
Yeah, right here. So
yes.
See, for example, that man's chest, you have it like multiple times.
Yes. So this is a design choice. When we have so when we identify that a semantic meaning is correct or potentially correct, we can put only one of the answers in the set, or put all answers that share the same similar semantic meaning in the set, right?
Okay.
So we're doing the second way. We put all answers sharing similar semantic meanings in the set.
Right, but here it's not. Is it maybe I'm not seeing it right, but here I see answers that are not just semantically the same, but they are exactly the same, or not, or no.
Yes, yes,
Okay.
yes. So, so we can actually reduce this one, reduce the this duplicated exact match. For now, I just demonstrate all of the answers that we put into the set. Yes, but definitely we should deduplicate the exact matches. But you are also correct that even with different passages, it's likely that the chatbot will be able to return
the same answer.
Yes, right. So like multiple passages might be useful for the generation process. Yes.
Okay, thank you
for the question. Yeah. So this is the one, and this is the kind of guarantee we can obtain. So say this user specified error level is alpha, the retriever error budget is alpha retriever, chatbot error budget is alpha chatbot, and we constrain that they sum up to alpha. Then we can obtain the following guarantee, that given a query, after constructing the retriever set, the most relevant passage will be contained in the set with probability at least 1 minus alpha retriever. And given a query and the most relevant passage, we can guarantee that the semantically correct answer will be contained in the set with probability at least 1 minus alpha chatbot. And overall, when we construct this, concatenating these two prediction set and construct that end-to-end pipeline, we'll be able to guarantee that given this query, and after constructing the two sets and combining the result, we will be able to contain the semantically correct answer with probability at least 1 minus alpha retriever minus alpha chatbot. And since these two sum up to alpha, it's just with probability at least 1 minus alpha. It's just this unibond.
Sorry again, for interrupting again. So this is alpha retrieval and alpha chatbot. Are they also determined by the user?
So actually, it can be definitely can be determined by the user. Our assumption is that the user only specified this end-to-end alpha, and we are going to optimize their combination so that we can improve the efficiency.
Okay.
This is the second step. We would like to find out the optimal combination.
Okay, nice. Thanks.
Yeah. So
hi, Shuo. I have a question.
Sure.
Is it okay? Yeah. So here, when you say query, what is this a single query or this is multiple queries?
This is just here I just indicate just one query, one question.
One question. Okay.
One question.
And the C query.
C query is the end-to-end prediction set. The prediction set after combining multiple this C chatbots prediction set.
Right. I see.
Yeah. Sorry for
I guess,
this.
Yeah. No. Yeah. I guess. Yeah. Sorry. I guess my question is, what is C chatbot here? Like, given query and passage.
C chatbot is actually this one. This aggregated
like here,
chatbot.
I see.
Yes. And the C
for
is
each
actually,
query. Sorry, for each passage retrieved, you append it to the chatbot context and get the chatbot output.
Yes.
And you aggregate that to a single set.
Yes.
I see.
Yes. So we will construct a chatbot set for each of this query passage combination. So for example, if we contain 5 passages, we will have 5 chatbots. And then at the end, we will we'll aggregate them together as the final output for the user.
Okay. Yeah, that makes sense.
Thank you. So the next step is what Mahdi mentioned. So we utilize Bayesian optimization to actually improve the efficiency. The basic idea of Bayesian optimization is that this one is based on sampling. So it is actually a good global optimization for non-convex, non-closed form objective functions. And also another very interesting property with Bayesian optimization is that it is compatible with any objective function, or in our term, efficiency function. So the user can specify arbitrary objective function, and our method will be able to be utilized to optimize that objective function. So overall, Bayesian optimization is a very suitable technique for optimizing the chatbot efficiency problem. And then in our project, for information, we define the efficiency function as the size of the final prediction set. We would like to find out, do the optimization so that we can get a small prediction set. And this is a demonstration of the Bayesian optimization. In the interest of time, I will skip for a moment. In the Bayesian optimization, to improve the efficiency, we do the following thing. We actually, given a data set, we divide it into two parts. The calibration set, which is utilized to construct a set, and the optimization set. This is for improving the efficiency, and then we assume that some efficiency function is specified by the user. Then for the first step, given the current error budget, we would like to construct a set and evaluate the efficiency on the optimization set. Like what is, for example, what is the average size of the prediction set? And then we will input the end-to-end set into the Bayesian optimization. And the Bayesian optimization is served to find potentially good error budget combinations for us, alpha retrieval and alpha chatbot for us for the next iteration. And this alpha, the sampled alpha, the potentially good alpha retriever and alpha chatbot will be input into the construct set again. And this iteration will be repeated for like n times. And the final output of this process is actually error budget, the alpha retriever and alpha chatbot that can obtain high efficiency, or in other words, obtain small average prediction size sets. So this is our way to improve the efficiency.
Well, if I may interrupt one more time,
Sure.
like how do you construct this optimization set?
So we would just split some part of the optimization set, calibration set as optimization set.
Okay.
So there's a little bit tricky part to construct the optimization set. We need to actually get the answers, the generated answers for every query passage combination. So for example, given a query, we will retrieve top 20 passage. So we have 20 passages. And for each of the query passage, we will generate 30 answers for that. So in total, for each query, we will collect 600 answers for that query.
Okay. And this will be the optimization set?
Yes. So this optimization set is basically used for evaluating the efficiency for the current alpha retriever, alpha chatbot combination.
Okay. And then you have to repeat this for all the other queries as well.
Yes, yes. Yeah. But this is just one for one time. You can collect the data for once and use that as a fixed set. You don't need to do that for every iteration.
Okay, I see. And then these optimal values that you find, they are like linked to the efficiency function, right? Meaning that if you change the efficiency function, obviously
yes,
optimal alpha values, they also will change. Okay.
Yes,
so
yes.
That means that so long as efficiency function does not change, you can stick with the.
Yes, exactly. Exactly.
Okay.
Yes.
I see.
Yes. To some extent, that one, this optimal combination is also determined by the distribution. But the distribution and also the efficiency function.
Right.
Yeah. Okay. The next ones are experiment. I will go through it a little bit in a little bit faster pace. We evaluate on two kind of models, ChatGPT, and also fine-tune Llama 2 models. So black box and the open source. We utilize DPR, the retriever trained on multiple data sets. So for all of the data set, we actually use the same DPR. We evaluate on 3 data sets: natural question, trivia QA, and the squad 1. All of them are short form question answering, short form but open domain question answering data set. And for each evaluation, we actually use 3 random seeds to filter out the effect of the random seed. And we evaluate on 5 coverage levels. And we also construct a set with PEC, probably approximately correct guarantee. And in this sense, we set the confidence level to 0.9, 90%. And we also play with prompt design a bit, including zero shot with instruction and in-concept learning with 2 demonstrations. We want to see how the prompt design will affect the result. And on each data set, we collected approximately 300 calibration data point, same for optimization data point, and 400 for testing data point. And for each query, we retrieve the top 20 passages. And then for each of this query passage combination, we ask for 30 generations from the language model. And we compare our method in the following baselines. The original one, RAG with the first retrieved passage, the passage with the highest retrieved score, relevant score. TRAC is our method. BOMF is our method without the Bayesian optimization. And the PEG BOMF is the BOMF method with the PEG guarantee. We want to see how the Bayesian optimization helps and how the PEG guarantee will affect the final result. Here are first are some quantitative results. We asked the first question we ask in this section is: do individual distributions satisfy the extendability assumption? And as we discussed, the most straightforward way is to actually see for each of those components whether the component, the empirical coverage level, satisfy the specified coverage level. And for an open source dataset, this is straightforward. So the empirical level is basically above or closely close to the alpha level. On ChatGPT, we can see that some of the entries does not satisfy the alpha level, meaning that they under covered a little bit. Then I actually play with more random seed. For this one is with 3 random seed, and I increase that one to 5 random seed. And we can see that after increasing the random seed, the coverage level regress to the required level. In other words, the immediate takeaway is that if we utilize more random seed for this experiment, on average, the coverage rate will be able to satisfy the required coverage rate. And this demonstrates that the exchangeability assumption actually is hold in this case.
Sorry, just one quick question. When you change the random seed, this calibration and optimization split changes, right?
Yes. Yes.
Yeah. Okay.
Yes.
And how many trials did you perform?
Okay.
How many random seeds did you try?
Yeah. For this one, this 3 is 0, 21, 40, 42. And after observing this undercovered, I increased that one to 5. And we can definitely do more. And I believe that with more random seeds, the level will be as closer to the specified coverage level. This is 5 more random seeds.
Yeah. Okay. Yeah, makes sense.
Okay. Mm-hmm. The second question is, what are the results on different data sets? So the immediate takeaway is that we actually observe the same trend with all of this. Another data set, the coverage level is basically satisfied. And means that the exchangeability assumption hold on this two data set as well. The third one is, does the guarantee hold for end-to-end? Because our ultimate goal is actually to obtain this end-to-end guarantee. And I actually evaluated this end-to-end guarantee in two ways. The first way is actually we only consider the golden passage. We calculate what is the rate that the golden passage is contained in the retriever set, and given the query the golden passage, what is the rate that the correct answer is contained in a C chatbot. And we can see that if we consider this end-to-end guarantee, the empirical coverage rate is close to the desirable one, which is labeled in black. And the one without peg guarantee is closer to the black one on average. So in other words, this end-to-end guarantee is satisfied by our method. The second one is more interesting from my perspective. In this case, I not only consider the most relevant passage, but all passages. This is the true end-to-end guarantee, end-to-end coverage rate we can obtain. The retriever set may contain the most relevant passages and the less relevant passages. And we utilize the end-to-end pipeline to construct a set. What I observe is that actually the end-to-end guarantee is more conservative than necessary, than required. For example, given that we would like to cover the true answer for 80% of the time, we can actually obtain a coverage level around 90% of the time. It's a bit conservative than required. And this can be explained by the fact that not only the most relevant passage can enable the chatbots to answer the correct answer, other passages may also be able to do the same thing. And when we construct the end-to-end guarantee, we only consider the most relevant one. So this explains why we can get a higher coverage level than our guarantee. If that makes sense to you. I mean, this is a
So is it because you may get the correct answer even with suboptimal contexts?
Yes.
Yes.
But when constructing a set, we only consider the most relevant one. We do not consider less relevant one. Yes. The next question is, how does the Bayesian optimization help? Here I report the result. So vanilla one is the TRAC one is our method. Bonferroni one is without Bayesian optimization. Peg bonf is the Bonferroni one with peg guarantee, and the peg TRAC is our method with Bayesian optimization and with peg guarantee. We can see that when comparing the one with and without Bayesian optimization, we can see that the average semantic size is actually reduced from, for example, 4.96 to 4.44 because of the Bayesian optimization. So given this, I guess it's fair to say that Bayesian optimization can be useful in improving the efficiency. And this is consistent across different data sets. The last one is, how does the prompt design affect the result? In our experiment, we designed two kinds of prompt. The first one is the zero shot with only the instruction. And the second one is in-class learning with two demonstrations. The immediate observation is that in the zero-shot way, the language model tends to answer the question in a more verbose way. For example, for this question, the true answer is actually the St. Lawrence River. And we actually asked the model to answer the question as shortly as possible. But it actually generate a sentence instead of just keywords. But in the prompt design case, the model just learns that maybe a keyword is just a preferable answer for this task. And then we also evaluate the coverage level for the few-shot prompt, and whether Bayesian optimization is useful in this setting, and the conclusions are consistent with other settings. The following are some qualitative results. So this one is the case where the language model, if we only consider the first one, the language model will just miss the correct answer. But by constructing the set, our method will be able to contain the true answer. I guess I'm running a little bit out of time, so I will skip it a little bit faster. So these are the results for the few shot. The first example demonstrates that there are cases where the model will be able to return the correct answer with the highest relevant passage, but our set will also be able to contain the true answer. But there are cases where only our method can be able contain the true answer. And this example demonstrates that after the Bayesian optimization, the TRAC, our method, is able to contain the true answer with less semantic meaning, a smaller set. Yeah, so this concludes my presentation. These are the takeaways from my work. The semantic clustering treats semantically similar answers similarly, and they claim that the semantic meaning is the more important thing we need to consider in constructing prediction set for language task. And we combining prediction set actually guarantees end-to-end coverage for the RAG task. And the Bayesian optimization actually serves to improve the efficiency of the end-to-end result. There are some limitations, like the assumptions with the retriever and the chatbot. In some cases, the assumptions may fail. And we also observed that the end-to-end guarantees are more conservative than required. To some extent, this is good. To another extent, this might be problematic. Depends on the application. Yeah, so this is all from my presentation, and thanks for watching, and a happy Halloween.
Yeah, thank you so much, Shu, for this great presentation. And sorry that I interrupted you multiple times. It was very educational. Learned a lot from it.
Thank you.
Yeah. Well, I have a few other questions, but I will reach out to you offline.
Sure. Let's think it like offline.
Yeah.
Thank you for this question.
Yeah, no problem. But if our only remaining participant, if he or she, I don't know, if he doesn't, no questions, then I think we can end the call.
Mm-hmm.
All right. Thank you. Yeah, looks like. Thank you again.
Thank you.
We'll be in touch soon. Thank you.
Yeah. Thank you.
Bye.
Have a good.
Bye.
Thank you.
Thank you.